Okay, good morning, everyone. I think we can just continue from yesterday. Uh, I think maybe at the last session, we could have maybe some exercise on chapter 14. I think you need to. I think you need more practices on that to prepare your quiz next week. So I think we can start the exercise later at the, I think maybe for the last 30 to 40 minutes we can have our exercise. But for now, let's continue a little bit on what we have done yesterday. So basically, whenever you see a questions that requires you to find a volume, for example, the volume has so the information given is the surface, the function of the surface, which means the function of two variables, z equal x squared plus y squared, so it's a function of two variables. And then it's also mentioned the region. The region means the area on that volume, base of that volume, which is bounded by some functions. So first, we are going to identify the functions on the base by taking times to sketch. So usually the question doesn't give you the picture, so you need to identify by yourself how the area looks like, the base of area looks like. So when you get the idea of this picture or the curve, after you sketch the curve, then you can start compute the volume by taking the double integrals and then set up the endpoints. Okay? So if we look here, this is y equal to x, this is y equal to x squared, and then first, usually we need to find these 2 points, which means the intersection points. So draw region and then identify function, include the intersection. Okay, include the intersection. So taking that into our context, we get x squared equal to x. So we can write so we have two intersection at x equals 0 and x equal 2, right? So that's how we get this is 0 and then this is x equal to 2. Okay? And then we can just put x to find y, it's 4, and then this is 0, 0. So this will be our two important points to set our interval. And then our choices, because we have at least two possibilities in double integral. We can set the integration as dy dx or dx dy. And I think if you see this curve, we can see this like if we set up this like xy like this, it means that this is going to be on the top, this is on the bottom, right? So if we set up the x as a constant, like from 0 to 2, so x will be outside function. So we could make the dy dx. Right? We can set up this as dy dx because see the arrow here is indicating that we are going to set up like, or you can just like imagine like a rectangle that move or line that move from 0 to 2, and it's moved perfectly fine. So in every interval we see that this 2x is always on the top of x squared on the interval 0 to 2, right? So if you want, you can identify d first in the terms of notation, that the x is from 0 to 2, and then y is from x squared to 2x. Because on this interval 0 2, x squared is always below, right? X squared is always below the 2x. So by this intervals for the d, then we can write So this is 0, 2. This will be x squared to 2x. And then we put the function x squared plus y squared. And then this is dy dx. Okay. And then we can write down the or compute the integrations. Let me put this on the left. So we start by taking the integration inside first, and if you are changing the integrations, you need to be careful because it's not a constant anymore. So we need to be, if we change this, then we need to change the endpoints, and then we need to select which are the most appropriate function that is going to be, if we, for example, if we want to change the dx dy, means that we are going to change all the functions in terms of, like, we have function of x, so we need to make it into function of y, which means that it will be different functions. Okay? So be careful on that. So let's just compute first this part. So we are going to compute with respect to y. So it will be x squared y and then plus y cubed over 3, right? And plug in the x squared and 2x. Okay, since we are going to expecting, like in the future, in the near future, for computing the double integral, we are expecting some complication in our math. To avoid some mistake, what I'm usually doing is I will take this into separate space, compute first until we get some simple equation, and then put back here and then integrate again. If you are dealing it in one complex integration, you can do that. But if you are not really familiar and if you are overwhelmed with the complexity, I think maybe you can separate first and then later you can combine all together. Okay? Because this is just a simple example. Maybe later we are going to deal with more sophisticated or more complex function. But still we are going to be able to integrate it. There is, I think, not necessary any, like, you need to use some techniques of integration. I don't think so. But maybe how we deal with the integration, maybe we are going to have a long equation, probably. So you need to be careful on that. So we put our 2x and x squared inside. So this will be x, let me write here. So 0, 2. This is x squared 2x plus 2x cubed over 3, and then minus x squared plus x squared with power, or is minus, over 3. And all this, still we need to integrate one more time with respect to dx. So we write on the right side, so this will be equal, so this will be let me write here 2x cubed plus 8x cubed over 3 minus x power of 4. This will be minus x 5 over 3. So 8 minus 1 is 7. 7 plus 6. So we can write, this will be x cubed x 4. Did I make a mistake here? Oh, wait. This one should be 6, right? So 6 over 3. So 6 plus 8 is 14. So this will be 14 over 3. x cubed minus x power of 4 minus x 6 over 3. Okay. Okay, and then we integrate. This will be x with power of 4 and divide by, so let me write here is x 4. This will be 12, so 14 over 12, it will be 7 over 6, right? 7 over 6. And then this will be x 5 over 5. This will be x7 over 21. So plug in 0 to 2, which we are going to require some calculation. You can just use calculators to compute this. And again, also to avoid mistake writing an equation in your calculators, I think up until this one should be okay. You can do the calculator things I think from here. It's safer. If you are trying to do from this part over, or maybe I think most of calculator, I don't know if your calculator can do multiple integrals on it. Can do? No, right? So I think maybe at the last part. You just use calculators, okay, to simplify your process. Okay. Because the principle is, I think, the first part here, when you set up the double integer. But this is I think the biggest percentage on all process. The calculation, like if you are make a mistake on that, not really that much, okay, the process. So this will be equal to, let me just write the end result. Okay. Now, if we look again, if we look again in the picture, maybe let me just give you the idea. Okay. That if we are going to use the, if we want to change like dx dy, I think we can do that, right? Because if we see from this side, the x squared here is the right side, always on the right side, and the 2x is always on the left side. It means like if you rotate this, the x squared is always on the top, 2x is on the bottom if we rotate the picture, right? So you can also do the dx dy's. But to write the x dy, we are going to change the endpoint and change the function. So which means we could write that this y equal to x become x equal half y, and this x will be equal to square root of y, right? And then we are going to have the endpoints from 0 to 4 for y. Okay, so we can write the d. So if using dx dy, then d, we can write that the 0, y, 4, and this will be half y, x, square root of y. So the double integral will be, or so this will be 0, 4, half y, square root of y, and inside is the same function, right? And this will be dx dy. And again, similar calculations, but now you start from dx first, and then later dy, and then put the endpoints, and the result is the same. The result is the same. But I think it's up to your preferences, which one is okay with you. As long as your setup is correct, you should be able to solve it, and it will be the same result. Okay? And if you look at the graph, or what should we have done here, so this actually, our surface, which is our paraboloid, a paraboloid with a circular, has its area here. So we have a paraboloid, and we have the 2x and x squared on this side. Okay? So if we look on the top, that will be our area, the plane. And the volume is here, like this green color. Or I think I prepared the graph on the other webs. Let me check with this one. So if you use the GeoGebra, okay, maybe it's not really clear what we have done here, but if you look at this, it's actually, we set up something around here that is our volume, because it is not fully stretched, the paraboloid, so it's actually going forward like that. So we are going to have like the volume. You can check using the GeoGebra if you want. It's very easy to set up. Okay. So this is the volume. Okay. So let me write here that this is the. Let me make it bigger a little bit. So this is the solid. It's a solid, solid volume. Okay, another notes for another example is if you have this, okay, like the question is evaluate double integral of x, y, dA, and you have a line equation and another parabola, but this parabola is in y squared equal to x plus 6. So the parabola is expecting to be going to be like this one. Of course, within this parabola, first thing before we try to identify and sort of compute the integration, you need to be able to sketch first. You need to be able to sketch how to sketch this parabola, and now it's in y squared. The easy way is probably taking it simplified. So 2x is y squared minus 6. I think using this expression and maybe simplify into x equal half y squared minus 3. This will be more sophisticated to check. It means that y squared multiplied by half. It means that the scale changed a little bit, and then move to the left 3 units. So from this vertices, the 0, 0, from here 3 units minus 3. Okay. And then after that, we get this point from our equaling the line and the parabola. Okay. So find the intersection. So again, the intersection. So equaling the x. So we can write it as x, y plus 1. So we can equaling x. So half y squared minus 3 equal y plus 1. So we get half y squared minus y minus 2 minus 4 equals 0, and we can simply set this up. This will be minus 4 and plus 2. So y is 4 and y is negative 2. And check again each y to find the x, and we get this point. Okay. So find intersections to get the interval. Okay, and then if we want to make it dy dx, so which means that we are going to using this, there will be a problem which we are going to be trying to how to solve that. For example, if we take here, we are going to see that at this point we are going to see that this will become a 2 area. So this is area 1, this is area 2. In area 1, this is the same curve, right? The same curve. So the top and the bottom, they are the same curve. How we deal with this? So one example, if we are trying to take the sy, then we are going to take the y squared into 2 different square root, because we have positive and negative, right? Plus minus, if we take the square root. So this one is the positive one, and this is the negative one. So we could see that maybe if we take both of this and then try to make it into our equation, maybe it will work. And it works, but you will see that the method will give you so if we try using, let me right here, using dy dx. So first we could see that the function, let's say the function is g1, that's supposed to be on the top. So g1 can be 2 different functions, which we can see from here. Let me write here. So this is 5. And this is 1. Okay. So so we can have g1 can be negative 2x plus 6. It means the function on the bottom. Okay. And then it can also be x minus 1. Okay. If the interval is from negative 3, x, and then negative 1. And this is x minus 1 from negative 1, x, and then 5. It means that 1 and 2. Okay. So that's the bottom equation. The top equation is this. Okay. So g2x is the positive 2x plus 6. Okay. So okay. So if we try to calculate, then we are going to have at least two double integrals. So let me write here that the double integral of x, y, dA, I think to it's right on the left. So the first is so the first is setting up from negative 3 to negative 1. Why is this so troublesome. Okay. -3 to -1, and then setting up from -2x plus 6 to 2x plus 6, like that. xy dy dx, and then plus. The rest of it is from -1 to 5. So this area 1. So this is area 1. The second one is area 2. And this will be from x minus 1 to square root 2x plus 6 xy dy dx. So a little bit complicated. So this is area 1, this is area 2. So this area 1, this area 2. Okay. So we could split up this and then try to separate the double integrals, and then we can try to compute this. But this is not what I'm suggesting. You will have trouble calculating the square root here, which maybe it's doable, but I'm not suggesting to use this method. And you have like two double integrals, right? It's not as convenient as we did in the previous example, right? So instead of using the dy dx, it's better just to use the dx dy, which we see from if we rotate there. So this will be on the top, this will be on the bottom, and we just only have one double integral. So we stay in dx dy. I think that will be better, right? And then change all in terms of y, the function. So function of y. Then this is the one that I think generally easier to solve. Okay? So we state from -2 to 4, okay, for the y. Okay? And then this one is from half y squared minus 3 to y plus 1 of xy dy, or dx dy, sorry, dx dy. And then I think we can just try to solve this. So we solve with respect to x first. So half x squared y. And then we plug in y plus 1 and half y squared minus 3 to the x. So and we write half outside like that. And then x squared will be y plus 1 squared y, and then minus half y squared minus 3 squared y. dy. And then, as usual, if you have reached these conclusions, you can compute using calculators to get the results. The result, if you check with calculators, it's equal to 36. So again, there will be some like this, like for example, this one is if you are like know the sketch, know the curve, and then whenever you see the curve, and then you need to try like you try the dx first, okay, and then try the other one. It means that if we have this, it is obvious that okay, if I have like for example here, trying from here, like you see this already, it's a one curve, but it's the top, the bottom, so like it's getting like we don't get the idea, right? So try to rotate, like immediately try to rotate and then see, oh, I think it's better to have this top and then this bottom. So just use that. But still, it's doable. Like if you have area 1, area 2, and then you need to simplify this one curve become 2 curve. Okay. Another example is this. Okay. So you're given the double integral. We have sine y squared and then dy dx. And then we also have the endpoint. So x is from 0 to 1, and y is from y equal x to y equal 1. So this means y equal x to y equal 1. Okay. As we see from the picture, this is how it is. Y equal x is here, the line, and y equal 1 is here. And to get into the how we can approach that dy dx is practically we are going to see the integral x from 0 to 1. Okay. And we are going to move according to the change in y. So change in y is from this line to that y equal 1. So you see, okay. Now if you try to solve this, like sine y squared dy, can we solve in integral? Can you solve the sine y squared? Which method we can try? If it's only sine y, I think it's okay, right? We can write that, oh, it becomes negative cosine. But can we do something about this? Unless we have maybe y sine y squared, that is doable. We can use substitutions and cancel the y. But there is no other components here, only sine y squared. Okay. And it's not the same as sine squared y. Not the same. Okay. This is the square is only in the inside, not the sine. So sometimes if we see some integration like this, like it's obvious, like when you see the question, and it's a typical question in chapter 15. And this is my shortcut to give you idea how to solve. When you try to solve and you think like no other simple method to integrate, then try to change this order. Okay. So this is dy dx. Try to look at dx dy. Maybe it can be solved. But when we change the order, we need to be careful on the endpoints. So we need to change our perspective. This perspective is x as a constant. Now we change. Y will be a constant. So from 0 to 1, that will be our constant. And we are going to see which one should be our functions on the endpoint. So let me write here. So let me just write some notes here. If double integral seems difficult to integrate with simple method, try to change the order of integration. So this is change the order of integration. So let's write the question first. Is 0, 1, x, 1 sine y squared dy dx. So this is, let me just write first to get the idea what we are dealing with here. So the x as a constant from 0 to 1, and y is from x to 1. Now we are going to change the alternative. Okay, let me copy this. Wait, copy and write here. So let's say we are going to have from there. Okay, we try to make out from there. So it will be taking the dy, okay, as a constant. So we can write also d if we take the y. So y, we can clearly see y is from 0 to 1. Okay. So 0, 1. And then what's happened with the x? X will be, we write here, x will be start from 0 to y. So we think from here and we move to the right for the x. And if we look at the functions, it's always going to be the top. This is the bottom, right? It's the same as we look like this. Okay. Do you see? So this is the top, this is the bottom. That's why we have 1 and then 0. And the previous one, this is the top, this is the bottom. But we change our perspective. Now this is the top, this is the bottom. Rotate your hand like this. Okay. Or if you prefer like right, left, the same. But usually for me personally, I prefer like top and bottom. Okay. So it's like okay, the idea is the top always always writing the endpoints, and then this is the other endpoints. So then we can use this to change the order. Okay? To change the order. So it becomes from 0, 1, and then this will be 0, y. This is sine y squared dx dy. And now I think we can solve it. And if we integrate with x, it doesn't have any x, so we can just add x, right? So again, it's x sine y squared, and then just plug in 0y, and then this will be dy. And then right here, and plug in y and 0 into x, so we can just write y sine y squared dy, which I give you some clue. If we have y, we can integrate easily using substitution method. So that is like substitution and integration by parts is, I think, the most common technique in integration, that sometimes you need to use that in our multiple integrals. Okay, so try using that to solve this. So taking the u is y squared and du will be 2y dy, so dy becomes 1 over 2y du. So substitute this to here, and we can finally write that this will be half, and all the things become sine u du. Okay. Or if you want to write, I think because 0, 1 is still the same, so when y is 0, u also 0. When y is 1, u also 1, right? Because I think no change, right? So still 0, 1, so it's okay. Now half, this will be cosine or negative cosine u from 0 to 1. So we can write here this will negative half cosine y minus 0, or we multiply both sides, so this will be that. Okay. So the indication is whenever you see the integration seems any method is not work, rather than trying to force out your way, change the order. Okay, change the order. Change the order. Directly, okay, just change the order. And I think you can change the order all the time. Like you can prefer like, okay, if this dy dx, what happens if I have dx dy? And you can choose like, oh, which one is easier. And for this one, we can change the order and then we can solve. Okay, now another note to finish off this part. There are some property. Okay, so this is property. So there is some property here that if we look at the picture, if we see the left one, maybe it's not really clear which one is the curve, like which one is the top, the bottom. If we take and then we rotate, also a problem here, right? This one is having a problem. Which one is so the idea is with any curve you can have, you can always take it separately. You can take it separately and then make it d1, d2. So you have two areas that you can specify. In area 1 here, d1, we can see that okay, this is the top and this is the bottom. And in the second one, you can see this is the top, this is the bottom. If we look at, so this one is dy dx, this one is dx dy, and it's still okay. It's still okay. It's still, we can write in terms of this. Okay? So we can just write the whole thing can be separated. Can be separated. Okay? And then another note is the double integral also, because we use that to integrate the function of the surface with respect to the area. We indicate that will be a volume, but we can make that if we have this picture here, this is the surface, and we take the surface as a constant. Just take it as z equal 1 or any number or any constant, which means that because this is equal to a constant, then the height will be a constant or is equal 1. So if we take this as our z, our height, then the volume is the base multiplied with the height, right? The volume of the solids. Or if we have this, it's actually the area itself, right? Because the height is only 1. So the volume is equal to the area itself. Okay? So the volume that we think that we previously stated as a volume of solids, if the height is only 1 unit, or at number 1, only 1. So it's actually the area itself, right? So we can actually write the area as a double integral. So this also can happen. And one last note on this double integral is we can also have a comparison property, just like in our calculus 1. So if we take this into, so if we have this, so let's say we have a plane, the small m, and then another plane with capital M, and our surface is in between. Our function is in between these two m, okay? And then it has the same projections, the same area. Okay? Now we can compare this tree. We can compare this tree, and then we can state that for all xy in the area E, then if we multiply the m with the area and then the capital M with the area, then the result in between is always in the middle. It's always in the middle. So what's the application of this property? This can be used for approximation and estimating if we have perhaps some value that is okay. It has to be maximum at this number, and then this will be minimum at this number. So our function should be in between those two numbers or two estimated values. So we can estimate, okay, it should be in between. So that's I think the last note for the double integral. Okay. So exactly as the bell rings. So okay, we continue. Now I will practice a little bit chapter 14. Okay, so we can have more idea what kind of question that we might have. So the first one is about limit on a function of two variables. So let's see the limit first, and I think the idea should be, it is very simple. The first thing on limit is always check. Always check. For example, we have 1, 1. Just check here. If you can find the number, okay, so it's done. Finish. Okay. So the first one is okay, right? It's 2, and it's 1 plus 2, so 2 over 3. So we can have the value. Okay, we get the result. Right? We have the limit. But here we have 0 and then 0 over 0. So when 0 over 0 happens, remember that every time we do like approach the limit, for example, we have x, y to 0, 0, 0. We can have many possibilities, right? We can create any functions and then we try to getting close that function into the 0, 0. What kind of function that can be like it is possible to get close, we can use that. But what I'm suggesting is just use a simple function. For example, we can state like the first one, maybe x is a 0, and then maybe we can have another one is like a fixed constant. Like for example, we can state that. So we can state that. So this is the. So we need to get closer to x to 0, y to 0. We can try to state that x and then 0. Okay, so we are going to have the x as a constant, and then the one that has a number is a y. So y getting closer to 0. So when this happens, let me write maybe, so limit, this is x 0 to 0, 0, which means that we are going to keep x as it is. So we have x squared, and then the top, because we take x and 0 inside, it becomes 0. So it will getting close to 0 first rather than any other number. Okay. You can check with another possibility, but I think it should be the same, like 0y, for example. Now we're taking, this is 0, and then this will be y squared at the bottom. And this is also 0. So perhaps we think, okay, maybe this is, because it's equal, maybe this is the result. But my suggestions, you can always check using use y equal x. Okay? Use y equal x. Use this function. Okay? It's still simple function. So we could state that the limit, because we are taking y equal x, so we are getting x. Okay? Oh, wait. I make a mistake here. It should be xy. And it should be x0. So sorry. Why I'm writing like that? So sorry. So xy to xx. Okay. So when this happens, so 2x and then multiply with x, and then x squared plus x squared, or 2x squared. So when this happens, this will be 2x squared over 3x squared, or this is 2 over 3. Now you'll see that this is 0, 0, and it seems like different value. So when you see different value, then we can take limit does not exist. And you can use like many functions, like just use the simple one like y equal x, or y equal x squared, or maybe y equal x cubed. Okay. Sometimes you will see that whenever you see different value, then okay, we are going to make a conclusion. This limit is not exist. Okay, this 4 number is asking second partial derivative. What does that mean? We need to derive twice. And remember, because it's partial derivative, we can have 2 possibilities, right? Partial with x, partial with y. And then we have partial xx, partial yy, and then partial xy. At least 3 different partials. Partial xy and partial yx is the same, so we can just use only, I think, get just which one we prefer. So fine, for example, let's look at maybe number 20. Number 20, let me write here. So we can write z is x e negative 2y. So first we take partial x. This is just e negative 2y, okay. And then partial y will be negative 2x e negative 2y, right? And then partial xx, since no x in the partial x, so 0. And then partial xy is negative 2 e negative 2y. And then partial yy is negative 4, or now it's become 4 x e negative 2y, and then this will be the 3 expected answer. Okay. Okay. I think whenever you have like already familiar with partial derivative, okay. For example, we have here how to partial derive. Basically, if we take partial x, which means that we are only care about x, and the other variable we can just let them as a constant. We take partial y, we only care about y, and then x as a constant. Okay. So whenever you are familiar with this, I think this should be easy to simplify, right? Easy to solve. Okay. And another question, this one here, sometimes you need to show that this equation are equal, which means that you need to describe the partial works and then try to find out how to make this equal. Okay. So perhaps you can start by taking the partial x, partial y, what will happen, and then try to put into our equation and see whether it's going to be the same or not with the statement. I think maybe try number 23. Try number 23. So number 23, we have z xy plus x e y over x. We can start with dou z dou x. So this is another way to write, but this is actually the same as partial x, just zx or dou z dou x, same. So we can try to compute with respect to x. This will be y, right? And then, oh, where? Okay. This will be y. And then, what will happen now? Do we have, so we have here is with respect to x, so we have 2, so we need to take a product rule, right? So plus, this will be e y over x plus 1 over x will be what? Negative, right? Negative 1 over x squared, right? 1 over x squared. Multiply with x will be negative 1 over x. So e y over x, and this will be negative over x. And oh, y. Forgot to write y in the front. Right? Yeah, this is the result for partial x, right? And then partial y. You can also try and check whether my any mistake that I make, because this is 1 over x, right? We derive this bit, and then with x, so negative 1 over x, and then y is a constant here. E should be okay, right? So this will be x plus, now we can just write, so x, e will be e y x, and then this will be over x, so you can just erase that. Okay. Yeah, I think the second one is easier. Now we take the statement and then multiply with x and y. So we multiply x with dou z dou x. So this will be xy plus x eyx minus, I multiply with x, that, and then y. This is xy plus y e y x, and then we need to plus this 2, right? So plus the 2. So just plus and see that we can cancel this. So we have what? So x dou z dou x plus y dou z dou y is 2xy plus xey over x, or this is there is some problem here. Do I have a mistake? Oh, no, it's correct. So this will be xy plus xy plus xey over x. The z is here. Z is this one. So this whole thing is z. So this is true. So confirm that we have correct statement. Okay. So true or proof. Okay. I think for this one the complexity is on the function itself. Be careful on this y over x. It's a little bit tricky, but still doable and not really take much time. I think the time that you need to take care of is the partial part here. I think we can move to finding the tangent plane. I think I will move to another page because it's too much writings. Okay, any questions before? Any questions? Okay, let's take a new page and we wait, is the let's crop this. Okay, find equation of the tangent plane and the normal line. So let's say, or I think you can choose which one you want to try from this 5 equation. Which one? 26. Okay, 26. So let's try number 26. Or do you want to try first? Let me give a couple of minutes to try, just to check. Okay. So how to find tangent plane? So we have z, right? We have z. So the idea is actually we're taking partial x, also we're taking partial y, right? And then afterwards we need to get into the equations. The tangent plane equations. And then we need to also first observe. Okay? If you see all the other questions, for example, number 25 and 26, it's in the form of z equal 2 variables. So we can limit that to 2 variables. But the other 3, it has 3 variables. But actually, the process works the same. So you need to find partial first. Okay? Partial x, partial y, and if you have 3, also partial z. And then you have the points, right? You have the point. You see that we have the point in number 26, 0, 0, 1. This is going to be, like if you have a line equation, you have like y minus a constant equal the slope, x minus something. Right? So we are writing something similar to that. But we have more than 2 or 3 variables. Right? So first we see that here, for this one, we say that the z is a function of xy, right? So we could first try to find the partial x first. Okay. Partial x is only this, the same, right? So the same as the function itself. And then partial y is we differentiate cosine become negative sign, right? And this is negative sign like that. And now we have the point, right? We have the point. Remember, when you do the line equation, you have the slope. The slope is the first derivative, right? At that point, remember, you want to find the slope, like you have a curve. You want to find slope at 0, 0. And then to find the slope, which means you need to put the point inside the equation, right? Now the same. We have the partial x, we have the partial y. Think of this like a slope, like a slope. Okay? It's like a slope. Which means that we need to look at the point. Okay, then we can just put the point here. X equals 0, y equals 0. And this is also the same. And let's compute that as a number, right? As a value. So at 0, 0, this will be 1, right? And this is also at 0, 0. This will be 0. So the equation of tangent plane for this kind of question is basically z minus the point is 1 equal the partial x, and then x minus the point is 0 plus partial y, the point is 0, 0. Okay. And since the partial y is 0, so we can make this 0, and we can just focus on the first part. So this will be z minus 1. So partial x, we already compute at point 0, 0 is 1, so 1, and then x minus 0. So the equation will be z x plus 1. Let me move this a little bit to the right side here. Okay. Okay, between 27, 28, 29, which one you want to solve? Okay. 9, okay, 29. Okay, so we are going to see the differences when we have the z as a function of 2 variables, and we have a function of 3 variables. How do we deal with that? Of course, we are not going to use another variable to write, okay, maybe w is function of 3 variables. We don't need that. What we are going to do is we are going to express partial derivative directly from these equations. Okay. So we can partially derive. We can use implicit. Okay, we can use implicit. So number 29 is sine xyz, and you need to be careful on this, okay, because it's simple but not that very simple. We can state and use just maybe state capital F xyz and write in one side of equation. Let's say x plus 2y plus 3z minus sine xyz. Okay, you can try this one, or if you want to partially derive directly using implicit, it's also possible. Okay, but I will just write this, and then I will write partial x like that. So this will be 1, 0, 0, and then this will be I will have, oh, why I am using this comma? This is just xyz, sorry. So it will be minus cosine, right? Minus cosine xyz, but we are going to derive the inside equation. So this will be yz, and then cosine xyz. Okay. And then we can input the point is 2, -1, and 0. And since we have 0, this will be very interesting to solve. So 0 as z, so it will be 0 because of yz. So this will be 1. Okay. And then partial y will be 2. And then the same, we are going to have xz now. And then cosine xyz. And then put the point. And again, because of the 0, then this is going to be 2. And then partial z is 3 minus now xy. And then put the point again. And then 0 here is cosine 0 is 1. So this will be 3 and 2 minus 1. 2 minus 1 we get minus 2. So 3 plus 2. Okay, 3 plus 2. It's 5. Now we have all these 3 partials. And again, we can think these 3 partials as our slope. Okay, as our slope. Similar to what we have in the calculus 1. Now how to deal with this is practically let me resize this. Okay. So this will be, I think we can write, let me write the equation first. Partial x minus a plus partial y minus b plus partial z minus c, and this is equal to 0. Okay, so we are going to input all the numbers that we have now. So 1, and then x minus, what is the point is 2, and then plus 2, y plus 1, and then plus 5, z minus 0. And then we can just simplify this. So this will be x minus 2 plus 2y plus 2 plus 5z equals 0. And then we can see that this will be our tangent plane. Oh, I think I forgot to answer the second question about the normal line. So the first question asking the tangent plane, which is this and this, the tangent plane. The normal line, in our case, usually, you need to write the symmetric equation. What is symmetric equation? Practically, symmetric equation is for this one, for this one, the symmetric equation, so symmetric equation for normal line is, for this one is, see this x minus 2, y plus 1, and z minus 0, and then see 1, 2, and 5. Okay? So what we are going to write is x minus 2 over 1, y plus 1 over 2, and z over 5. Okay. You can try to simplify it if you want, or just stay as it is okay. It's also answering the normal line. Okay. Or if you want, you can write a parametric equation according to that statement, that x will be 2 plus t, and then y is -1 plus 2t, and z is 5t. But if you end up until the symmetry, it's okay. It's already correct. This is another additional. How we can get this parametric? We can equal all this with t. So x minus 2 equal t, so x will be 2 plus t. And then y plus 1 over 2 equal t, so y plus 1 equal 2t, so y is 2t minus 1. So it's actually equaling to t. And that's why z over 5 equal t, so z is 5t. But that is if it is being asked. Okay? If not asked that thing, if the question asking only tangent plane, so I think this one is the answer. Okay, that is for tangent plane. So tangent plane, at least we will have as a conclusion after we did some previously in some section. There is only, I think for now you can see two possibilities for tangent plane. If you have z equal function of two variables, then you can go for this case here. And you can write z minus the point, and then this is partial x and partial y, and then this is also inverted point, right? Or you have three variables. When you have three variables, you can build one function first that express these three variables, and then partially derive x, y, and z. Okay, and this partial will be put into this equation, which is this tangent. Okay. Or you can just think this one, okay, because this partial z for this one is 1. So z directly, right? Same. So you can just think this. Very simple. There are a lot of like steps, but finally you can just use this to solve all the tangent. Okay. I hope you understand. Okay? Because sometimes, like in calculus, like you have like several methods, but at the end there will be some simple method that can work for everything. Okay. Like in tangent plane, you can just using this, and okay, from this three, it's like number this is like a lot of numbers, but let's see what will be which one do you prefer to work on, 27 or not? I also confused looking at the numbers, but it's doable. It's doable. Any suggestion which one we should start? 38, okay, 38. Okay, so basically this is writing all the possibility for the chain rule. So for example, we have W is a function of PUP, and P is function of PQRS, U is function of PQRS, and the P also PQRS. So we have a 3 branches tree, and then later branch 4. So we can start number 38 by writing W at the top, and then it's branching out become T, U, and Phi. Okay, and then as TU Phi is all branching into each one getting 4. So P, Q, R, S. This is also P, Q, R, S, and this is also the same P, Q, R, S. So the question is asking, write all the chain rule for all differentiable functions. So we are going to take our time to find a path. Okay? So for example, we find a path going through here, we go here, okay? Every time you get the line, this will be partial of that function with respect to this, okay, dt. So for example here, let's see that this one is partial t, okay, and then this is partial p, like that. So the chain rule we are going to use to describe, for example, every time you have these branches, the chain rule is actually the first and the last. To make that, we are going to multiply the middle. Okay? So look here. Okay? So we write for all the things that has partial w with respect to partial p, like that. First, we have this red one, right? So we write here, and then we also have wp here and wp here. So we have three components. Okay, and then write all of that. So this will be. This is a good question to understand the branches. And then plus, this will be WU, and then WU, WP, and then plus W, WP, WP, WP. Okay. And basically, we are going to write all the same thing with WQ. Let me write this on left here and make it a little bit smaller. So this will be W. Okay, and then WR. And we will have four possibility, right? This will be what? U. And then the last one is S. And then done. That is all possibility. And again, to confirm, we can check all the paths, okay, all the possible paths. So this is the first, and then the second one here, and the other one, and then the other one, and second here, all the branches we check. Do you want to try number 39? It's like a simple, but yeah, interesting because it has a function form that is not explicitly describe what kind of functions. Number 39. Okay, so we can write here. Let me make this smaller. Okay. Okay, 39. We have z, and then we have z is y plus f, and f is a function of x squared minus y squared. So x squared minus y squared is a function inside the f. And we state here, the statement is f is differentiable. So we assume that we can derive the f. And then the question is, we need to prove that if we take y, multiply with the partial z with respect to x, and then plus x partial z with respect to y, it should be equal to x. So we need to find at least these two partials, and then we substitute, and then we need to prove whether this is true or not. So the first thing is we see the z. Okay, let me write z again at the bottom side here. If we try, for example, if we try to partially derive this with respect to x, what will happen? For y of 40 will be 0. But what happened with this? If you have f of x, you derive that, it will be f prime x, right? So think similarly like that. So it will be f prime x squared minus y squared. But you need to multiply with what? Let me change the rule. See this first. Okay, so if you have y equal f of x, y prime is f prime x. Okay, very clear. So if we have this is right. Okay, so similarly with that, we are going to have f prime x squared minus y squared and multiply with 2x. Or we can write 2x f prime x squared minus y squared. Okay. And then the other part, we have partially with y. Okay, so y become 1 plus, now it's the same thing. So f prime, and then this will be x squared minus y squared, but multiply with 2y. Or it's negative 2y, sorry. So we have 1 minus 2y f prime x squared minus y squared. Maybe this will be better if I write negative 2y like that. So we multiply this with y. We multiply this with x. Okay, and then we write that x, or the result is 2xy f prime x squared minus y squared, and then plus x minus 2x y f prime x squared minus y squared. And since this is the same, we can cancel this too, so that the result is x. So it's true that y dou z dou x plus x dou z dou y is equal x. So true. Yeah, this one. Yeah, this is like if you have a function inside the function and you want to derive, you are going to write f prime, and then you still have the function inside, multiply with the derivative of the inside function, right? With the chain rule. Similar with this, when we have f and then we have a function inside, it means that when we derive with respect to, for example, with respect to x, then we write this as it is, f prime, and then has something inside, multiply with the inside function, derive with respect to x. So multiply with 2x. Same thing with this one. But now we are going to use y. So f prime, use the same as it is, multiply with the y squared, derived becomes negative 2y. Right? Negative 2y. So we are going to have like 1 negative 2y f prime here. And I multiply x and y because I want to prove this. Okay, I want to prove this, okay? Because it's already mentioned in the question that show that this is true. Okay, So, okay, we need to multiply with y and x, okay, to make it true. This is part of the question, okay, part of the question.
So you just put that equation over there, like, as an example.
Yeah. The right one is this is just an example.
It's not about the...
Yeah, it's an example, okay. Example.